Hello students, welcome to the next lecture on the testing of hypothesis. Today we will discuss about monotone likelihood ratio, which is a part of the UMP test, uniformly most powerful test. We will discuss both the discrete and the continuous variable. Myself Dr. Gar. You can simply follow my YouTube channel Dr. Harish Gar for the probability and statistics. Otherwise you can simply scan this code for my Telegram channel link. So what we will discuss in this lecture, we will see how you can test the hypothesis for some parameter under the conditions that h1 is off for the one-sided. Either h1 will be here or it can be this one. So accordingly h0 can be adjusted. So remember that in our last lecture we already discussed the testing of hypothesis when it is of the equality form. So you have remember that whenever you want to test the testing of the hypothesis of the equality form, then we always working for the most powerful test. However, this is the most powerful test whenever there is a equality form. On the other hand, whenever the testing of hypothesis are either greater than, less than or not equal to sign, then we always working on the uniformly most powerful test, because h1 is called as the compound hypothesis. But how you can deal with the UMP test? But in general, the uniformly most powerful test does not exist for the one-sided. So it doesn't mean that we can't find the UMP test for the one-sided testing problems. Although in order to existence of the UMP test, there is certain kind of the family of the distributions for which these UMP test will hold. So it means we firstly need to satisfy what is the family of the distributions for which this UMP test existence in nature. So that family of the distribution is called as monotone likelihood ratio property. There is a distribution is there. The distribution means either the binomial, normal, gamma, beta or any of the distribution. If that distribution, family of the distribution satisfied this property, then we call it the UMP test exists, otherwise not. So it means in order to understand this UMP test, there is a must necessary that you have to understand what is a monotone likelihood ratio property. It is called as the MLR property, monotone likelihood ratio property. So what is that property? This is the ratio of the two probability density function. If it is the discrete, then it's a ratio of the two probability mass function. Or you can say if the two distribution f and g will accept this property, it means for every x1 which is less than of the x2, this ratio, that is the ratio of the density function at x1 is also less than of the x2. That means the ratio is my non-decreasing in the argument x. Or you can say once is how you can what is the meaning of the non-decreasing? How you can prove that f is a non-decreasing? When you prove that derivative is greater than or equal to 0, then it means the function is increasing. Or you can say it is my non-decreasing function. The same thing for here. If it consists of more than one variable, then you can take the partial derivative. What is the meaning of that? What is the meaning of this ratio and how we can use in the hypothesis testing? If the probability density function f of x will satisfy this monotone likelihood ratio property with respect to this another function gx. What is the meaning of that? Whenever you want to increase the value of the x, the more information is taken from the f rather than the g. That's why we say that this f of x satisfied the monotone likelihood ratio property. Means if you are increasing the value of the x, then the information about the distribution is taken from the f rather than the g. Based on this property, we can see if the family of the random variable or the distribution satisfy this property, then the uniformly most powerful test can be determined for the one-sided. Remember, whenever this property does not hold, then the UMP does not hold for the family of the distribution. Now here there is a one term which I use again and again, that is a family of the distribution. What is the meaning of the family of the distribution? So what is the meaning of the family of the distribution of MLR? Any of the real parameter family of the distribution is said to be monotone likelihood ratio in, what is the meaning of the Tx is? Tx is a function of the x. It can be summation of the xi's, it can be product of xi's, it can be log of xi's, or anything are there. It must be the function of the xi's. What is the xi's? x1, x2 are the random samples. These are my random samples element. Now when this property hold, first of all that probability density function exists, and the second is whenever, because the unknown parameter I have considered, this is not a conditional probability, this is my parameter. For example, if you know what is that, which distribution is here, yes, this is my Poisson distribution. So I can return this function as x, the unknown parameter is my lambda. So this is not a conditional probability, this is the parameter rather, or you can write this as x semicolon of this, that's the same thing for here. So whenever you consider the increasing, like theta 1 is less than of this and this ratio is a non-decreasing, then we can say it's a monotone likelihood ratio. And once this ratio will exist, is a non-decreasing, and it must be existence in the set of their existence. What is the meaning of the set of existence? That means either both the values of this are positive, and if one of them is, say if this number is greater than 0 and the denominator part is 0, then the likelihood ratio must be the positive value. That is the meaning of the existence. Now how you can check whether it's a monotonic are there, we will describe the two methods, and later on we will describe the 8 to 9 examples in this lecture so that you are able to understand it in a very fruitful manner. Firstly, we will discuss with the help of the definition. You can start always with the theta 1 is less than of this and take this ratio, and then your target is to prove what is the f is, this is the likelihood function. So we all know how you can define the likelihood function. We already discussed in our maximum likelihood function, we denote it as a L. L is nothing but my here, or you can define like here. This is similar to x with respect to the parameter. Once you define the likelihood function, substitute this value here, and your target is to prove this ratio is my non-decreasing. How you prove that it's a non-decreasing? Either you can prove that this number is greater than 0 for all the parameters in this tx, or otherwise you can prove that the derivative must be positive. That's the meaning of the increasing, that's a non-decreasing. The second method is, if you want to compare the value of this distribution function as a one parameter exponential family. What is the one parameter exponential family? There are the two different forms. If you write this, any of the function like f of x comma theta is in this form. If I start from here, what is that? This is my Poisson distribution. So can you write this form like exponential any e raised to power anything which is related to the parameter. So this is my parameter, but e raised to power is not with the t of x, so it is not in the form of here, and so on, where this q is must be the non-decreasing. We will discuss the next example. We will describe what is the explanation of this one parameter. Again, the second form is, instead of all the exponential, I can return as, because I need this red portion only, so it must be that a parameter and a function of the x, then it's the exponential distribution family. Now first of all, we will prove that this exponential families are my monotone likelihood ratio. So I can start with any one of them. Let's say I can start from here. So if I consider this is my density function. So what is the likelihood function? We can firstly define the likelihood function. This is my product of this f of xi of this. So what is that? If I consider here, if I consider the product of this, so this is independent of the I, that is x, so it is power of n. This is my, if I take the product of this, I varies from 1 to n. This is my xi, this is my xi. So this is independent of the I, this is power of n, and so on, and this is my summation. Now if we start from the likelihood ratio, what is that? If you take the ratio, clearly says that this number, because exponential part is always be greater than 0, this part, because theta 2 I consider as greater than of the theta 1, so this ratio is greater than 1. So we can say which is a non-decreasing in, what is the function of this is here, in this one, if q is my non-decreasing, because if it is less than 0, you have to prove that. Now we will discuss these several examples. So this exponential families, which consists of the normal distribution, binomial, and more are there. Make sure it has only one parameter fixed. For example, now let's start with the 8 to 9 examples in here. Let x follows the binomial distribution, because we all know that in the binomial distribution, how many unknown parameters? There are the two unknown parameters, n and p. If n is equal to 1, then this binomial distribution becomes my Bernoulli distribution. Fine. So we all know that if here this is my n is 1, so it is a binomial or the Bernoulli. Then you have to prove that it's a family. You have to prove that it's a family is a monotonic. Whenever there is a family, it means it is consist of this random sample. Fine. So once it's a random sample, firstly you have to define the probability mass function of the binomial. So what is the binomial is ncx p raised to power x 1 minus p of n minus x. So but n is my 1, so this part is my 1, this is my 1 here. Now it consists of the family, so it means you have to define the likelihood ratio. So the likelihood function is my here. The only unknown parameter is my p, so I can written here. This is the product of this, so I can write this as what is the product of xi's. This can be written as product of this, and similarly. Now how many unknown parameters? There are the 2 unknown parameters, so I can start from here. Let p1 is less than of p2, and we can define the ratio. What is the value of this? So I can substitute here. This is the p2 summation of the xi's 1 minus p2 n minus summation of xi's divided by similarly for the p1. Now I can take this pair. This is p2 over p1 summation of the xi's. I can written as 1 minus p2 over 1 minus p1 n, and I can written as 1 minus p1 over 1 minus p2, this one. So I can break them here. This part I can take this pair and for this pair as common. Now our target is to prove this number is greater than 0. That's a very simple. Look at C. P1 is less than of P2. So we need a 1 minus P2. So what is the meaning of the 1 minus P2? It is a less than of the 1 minus P1. Now if you product them, what is the meaning of that? P2 of this is also be less than of this. Fine. So what is the meaning of that? P2 of 1 minus P1 and over this. What is the ratio of this? This is my greater than 1. And what is the ratio of this? And you can see this P2 is my greater than P1. 1 minus P1 is greater than of this, and their product is also be greater than here. So it means this number is greater than 1. So ratio is also be greater than 1. So this number is my greater than. That's a positive number out there. It means this is my non-decreasing. Once it's a non-decreasing, it means it has satisfied the monotone likelihood ratio. Look at the second one. So consider this is a normal distribution. This is my mean. This is my variance. Look at the one parameter is my fix. Show that the family. Again, this is the family. So we consider the random sample. Firstly, write the probability density function of the normal distribution here with variance this. Because this of the family, so we can write here. So we can substitute this value. So this is independent of the I. So I can written here, and this can be written of this form. Fine. Now I can open this a minus b whole square. If you open this, you can written like it. Now you can see, you can compare this with the exponential family. You can see here e raised to power. Look at the two function. One is a parameter. Parameter is my mu, and t of x. You can see here. This is also a function of the x, but the coefficient is not the parameter of theta, that is a mu. So this is totally a parameter of the mu, that is the d of theta. This is a totally a function of the x, so this is my s of x, and this is my here. So you can see q is my mu, t of x is my summation of x, and q is my decreasing. Why? Because we consider that mu1 is less than of the mu2 r. So it means it has a monotone likelihood ratio. Second method is, you can start from here. You can consider mu1 is less than mu2, and you can define the ratio. So what is the value of the f? You can substitute this value. This part will be cancelled out. I can take exponential common. So you can see this part will also be cancelled out when you take in the upside. So you can write it here. Now mu1 is less than of the mu2. What is the meaning of that? Mu2 minus mu1 is my positive. This number is positive. What is this number? What is this number? So it means mu1 square minus mu2 square is less than 0. But because of this exponential part can never be negative. So it is always be a greater than 0. Hence it is a non-decreasing. And what is the function of the axis? The function of the axis is my t summation of the x size. Hence the family will satisfy the monotone likelihood ratio in here. It means whenever we will discuss about the UMP test, so UMP test of this distribution exists in the form of summation of xi. Look at this again, it is a random sample and the gamma distribution is given to you. So we all know that this is the density function of this gamma distribution. It consists of the random samples. So we firstly define the likelihood ratio as the product of this. This part is constant, so I can written like here. How many unknown parameters? You can see this alpha is my fixed, so I can consider alpha is my alpha naught. This is my fixed number, and beta is my unknown. So we can take beta 1 is less than of beta 2, and then we can define the likelihood ratio with respect to beta. We can substitute this value here. Alpha I can consider as the alpha node, so this is my alpha node. So you can see this alpha node will be cancelled out because it's a constant number. This number is not cancelled out. This number will be cancelled out because alpha node is a constant number. So I can simplify them. You can written like here. Now your target is to prove whether this is a greater than 0 or not. You can see that this number beta 2 minus beta 1 is always positive. Exponential part is always with a positive number, so it is a greater than 0. So what is the meaning of that? It satisfies the monotone likelihood ratio. The function of the x is my summation of xi's. Hence the gamma family for the fixed parameter of alpha has a monotone likelihood ratio. Now look at that. This is another distribution. Now you can see whether it's a family is given to you. No. So there is no family given to you. It means there is no need of the likelihood function as of this. What is the meaning of that? It means this is from 1 to 1. So 1 to 1 is same as that of this one. In this case, beta is known to you. So I can consider beta is my beta naught. Alpha is my unknown. So I can consider alpha 1 is less than alpha naught. So I can define the likelihood ratio this. So this is my here. So beta is my beta naught. I can substitute here. We will get this. This will be cancelled out. I can take this part in the numerator. We will get here. Now, because of this modulus sign, there are the two cases. It will be plus or it will be minus depending upon the values of this x, whether x is greater than alpha 1 or x is less than of alpha 1. So we will discuss the three cases. Either both are my positive, both are less than 0, or at least one of them is greater than and less than 0. What will happen if both are less than 0? It means this modulus value is my negative. You can see this number is my negative, this number is negative, so minus minus plus. If you open them, you will get this. And since alpha 2 is my greater than alpha 1, so exponential part is a positive, this is a greater than 0. Look about the second part. So x minus alpha 1 is a positive, so it means this number is my positive, this number is my negative, so this part will be my plus 1. After simplify, you will get here. Because of this exponential, it is always be a greater than 0. When both are positive, so it means it is my here, again it will be greater than 0. So in all these three cases, we will get this likelihood ratio as a non-decreasing. Hence, this double exponential family, because this is the distribution of the exponential family, is a monotone likelihood ratio. Look about the other one. Now again, this is given to you a family, so you have to define this likelihood function. In this case, alpha is given to be a fix. Firstly, it's a beta distribution. You define the probability density function of beta, define the likelihood function like of this. Now alpha is fixed, so I can consider alpha is my alpha naught, and you have to find the beta as a variable. So I can consider this and define the likelihood ratio. We can substitute this value. Since alpha naught I consider as a fix, so it will be cancelled out, or this part is my constant with respect to this I. So this is my power of n. This alpha naught cancel out b. This is my cancel out b, and here clearly says that beta 2 is my greater than of the beta 1, so this number is my positive, so this number is my greater than 0, because this is a real number, so which is a greater than 0. So what is the meaning of that? It satisfied the monotone likelihood ratio, and the function of the x is my here. It means whenever we are trying to find the UMP test, it will be in of this product of 1 minus xi. Okay, look at that. Now in this case, the family is not given to you, so you have to find the monotone. This is the uniform distribution. We all know what is the PDF of the uniform distribution is. When you have the A comma B, PDF is my here. Corresponding to this, what is the PDF? It is my 1. So how I can write this? I can write this in the form of that is a unit length of this. This is the notation of this. That is a to B. I can return this number also as 1 minus B over A of I A to B. Fine. Or otherwise I can return as 1 over B minus A. Whenever X lies between A to B, it is 1 upon B minus A, otherwise 0. So which is, now how many unknown parameters? There is only one unknown parameter. So let's say theta 1 is less than theta 2. Then we define the likelihood ratio. Now you can see there are two different parameters. You can see firstly theta 1 is less than of the theta 2, that is satisfied. So it means according to this we have the function of 1 when theta 2 is less than of here. Fine. While for this denominator part it is my 1 when it is of this nature, otherwise 0. So it means and theta 2 is always be greater than of this theta 2 plus 1. Theta 1 plus 1, now where this value lies, it can be of here, it can be of here, but it can never be lies outside that. It means there are the two cases. The first case I consider the value lies here, second case I can consider here. So let's say theta 1 lies, first I case here, which is here. Now how many intervals are there? So we can define this ratio in the form of this. Either it lies in this, it lies in here, and so on. Now what is the value of this? When X is less than of theta 1, remember this is the value of 1 and 0. This is the value of the numerator, otherwise 0, and this is the value of the denominator when X less than of here. So whenever X less than of theta 1, denominator value will be my 0. What is the numerator value? Is also be less than 0. So it's a 0 by 0, that is a undefined form. Look about the second case. When X lies here, that is this satisfied, so denominator will be 1, but look at that, in the numerator case the value is given to be 1 here, while in the denominator the value of this is given to be 1. So this is 1, while in this case the numerator value is my 0. So the case is 0 comma 1. Third case, when X lies between this to this. In this case, remember this is the value of the numerator 1, this is the value of the denominator, and it's a uniform, so the value lies in between them, it's a 1 over 1 here. Similarly, when it lies between this, so it will fall outside the domain of theta 1, so denominator part will be 0, numerator is 1, which is infinity, and so on. Look for the second case, and it means, what is the mean? This is undefined, this is undefined, so whenever the function is defined in these three cases, it's increasing. You can see whenever you have to increase the value of X, it's 0, 1, and then infinite. So it means it's a non-decreasing function. Look at the second case, when theta 2 lies between here. Then again there are the four cases. So remember, in this case this value is my 1 and this value is my 1. Rest all the values are my 0. So if X is less than of theta 1, so both the values are 0 by 0. When X lies between here, theta 1, that is the denominator is 1 but numerator is my 0. When X lies between here, denominator is 0, numerator is also 0. When X2 lies between here, numerator is 1, denominator is 0. When X2 lies here, both are my 0, 0. So this is undefined, this is undefined, this is my infinity, this is undefined, this is 0. So it means the value of function is defined only for these two cases, and again it is increasing because these values are increasing, so value of this function is also increasing. So again which is a non-decreasing in the interval of theta 1 to theta 1 plus 1 and up to here. So whenever the value lies between this to this is a non-decreasing. So both the cases we discussed, in both the cases is a non-decreasing, hence the UMP, hence the monotone likelihood ratio exists for this uniform distribution. Okay, so show that the Cauchy distribution is without the monotone likelihood ratio. We all know that the probability density function of the Cauchy distribution is here. The first parameter alpha is given to theta and beta is given to be 1. So if you substitute here as a 1, you will get this expression. Now there is one unknown parameters. Now is the whether the family is given to you? No. So there is no need to find the likelihood function. So we can define the likelihood ratio. We can substitute the value. This will be cancelled out. I can written like here. Now can you say this is always be greater than 0? You can't say that, because depending upon the value of the theta 1 and theta 2. So how you can prove that? We will take about the two different cases. First case is when x lies between plus minus infinity or x 0. So look at that. When x is 0, you can substitute here. What is the value of this? It is my 1 plus here, which is definitely be a greater than 0, because it's a positive number, it's a positive number. Fine. What will happen if x approaches infinity? So how you can do that? I can divide the numerator and denominator by x square, which can be written like this. Now whenever x approaches plus infinity, it goes to the 0, it goes to the 0, which is 1. When x approaches minus infinity, again it goes to the 1. Now can you say this number will goes to the 1? Can you say this number? Because at the minus infinity is number is 1, plus infinity is a 1. So if this number is a decreases and then increases, it is not a monotone likelihood. If this number is a increases then goes to the 1, again it is not a monotone like. So the only case is when it will be the uniformly 1. Can it be 1? Because remember that theta 1 is less than theta 2 and they are unknown. So you can choose theta 1 can have any value, say 5. Theta 2 must satisfy this property, say 7. Can this number be a 1? No, which is not equal to 1. So what is the meaning of that? The function is not monotone. Once it's not a monotone, it means the Cauchy family does not have a monotone likelihood ratio. So once it is not a monotone likelihood ratio, it means the UMP test is not exists for this problem, for this testing of hypothesis. Again, in this case, we have considered the first parameter as a unknown, second as a known. Say if we consider the first parameter as a known and second as an unknown, again show that they have the no monotone, this one. So in this case, I consider as alpha is my 0, so we can substitute alpha is 0 here. Now I consider again two unknown parameters, that's increasing. We can take the ratio, so pi will be cancelled out. I can written like here. Again, we can't say that it is increasing or decreasing, so we can take the two case. What is the value when x is 0? You can substitute here. It will be my theta 1 over theta 2. Fine. It can be, it is a positive because this is my positive number. So it is a positive number, that's fine. What will happen if x is plus minus infinity? So you have to divide it numerator and denominator by x square. So this is my plus 1. This is my plus 1. So what is the ratio is here. So you can see this part goes to the 0, this part goes to the 0, it is my here. But because of this number is greater than 1, and for x is equal to 0, this part will be here, which is a less than 1. So what is the meaning of that? It is not a monotonic. Hence UMP or the not a monotone likelihood ratio exists. Okay, another one is, again you can see that this is the I, that is the unit interval. What is the meaning of that? It means whenever x lies between pi 1 of this and of this, the value is my c of theta and h of x, otherwise 0. That is the meaning of x parameter, this one. Fine. Now you can see there is a family. There is a family, so it means you have to define the firstly likelihood function. So we can define the likelihood function. So we can see here, what is that? Why it is so? Because if you define the likelihood function, what is that? This is the product of c of theta, h of x and I of this. So if I divide it by product of c of theta 1 and h of x, because this is independent, so I can cancel out, and this range is with respect to the x theta 2 and this is theta 1. Now again we will consider two cases. because what is given to you? Pi 1 for the numerator part, this value is my here, this is my for numerator part, the value is 1 for the denominator part, this value is my here. Fine, the value is given to be 1, and given that these are my non-decreasing, so it means we can start from the here and up to here. So again there are the two cases, whether this lies on the left side or right side. So again there are the 4 cases, so we can discuss here. What will happen if x lies between here? What is the value of this? So you can see, again you can draw these function values. It means whenever pi 1 theta 2 here, pi 2 theta 2, that is from this to this, the value is my c theta of hx, and the value of this to this is my c theta 1 hx. This is my theta 2. So now whenever x lies between pi 1 to pi 2, it means this numerator part will be my 0 and the denominator part will be my here. So I can written as 0, because this part will be 0 divided by something is always be a 0. So the first part is 0. Second part is when x1 lies between here, so both the portions are there, so the answer will be c theta 2 hx divided by c of theta 1 of hx. Hx will be cancelled out, so it will be here, and for the last case it will be infinite. Clearly say that it's a increasing, because it's a 0, it's a positive number, and infinity, that's a non-decreasing. Similarly, if you look about here, what will happen? For the first case here, the answer will be my c of theta 1 hx, and for this case it is my c of theta 2 hx based on this definition. Now whenever x lies between here, what is the meaning of that? The numerator value will be 0, so 0 over something is 0. Whenever it lies between here, so it's a 0 by 0 because nothing is defined, and whenever it lies in here, denominator part will be 0, numerator is my hx. So it is my 0, it is my undefined, it is my infinity. So it means again it's a increasing for the well-defined function. So therefore it's an increasing function, so likelihood ratio exists. Okay, look at the last example. So if you consider the Poisson distribution, again a family is given to you. Firstly we will define the probability mass function. We define the likelihood ratio, which is here. We can, unknown parameter is lambda, we can start from here. We can substitute this will be cancelled out. I can take this as summation of the xi as a common over this, and I can take this as common plus of lambda 1 minus of this. Fine. Now lambda 2 is greater than of this, so this number will be my lambda 2 over lambda 1 is my positive number, is always greater than 1. This number, exponential part, is always with the positive, so the product of them is always the positive, which is greater than 0. It means the ratio is my likelihood, is a monotone likelihood ratio. So hence once you are trying to identify the UMP test, this property must satisfy. I hope you are able to understand how you can check for the monotone likelihood ratio. Based on this feature, we will try to see how you can identify the UMP test for this testing of hypothesis in our next lecture. I hope you can simply learn this concept. You can share, like and comment this video with your friends. Best of luck students. Happy learning.